Hello everyone, and welcome to CRPScontender, my complex regional pain syndrome education channel. Today's video is Hypocretic holes, isolated cataplexy. Now before we get into the main meat of this video, I want to do a quick refresher as to what CRPS is if for some reason you don't already know. CRPS is a severe immunoneurological disorder which affects the entire nervous system including the brain. It focuses mainly on your autonomic nervous system, which is responsible for your reflexive behaviors, moods, mobilization responses for dealing with threats, your maintenance responses for when you're feeling safe and secure, immobilization responses, which is dissociation or your freeze response, and your GI motility, which is the function and movement of your digestive tract. Now that bit of a refresher is out of the way, let's discuss cataplexy. Now in this video, I am actually going to start at the end with what it looks like and work our way backwards to why it happens. So, no, we're kind of going in reverse order here, but hopefully it will still make sense. And I know I usually try to insert humor and funnies to make it more tolerable, but honestly I'm having a pretty rough time with that right now, so this is going to be much more academic essay than humorous educational video. And I apologize, but if I try to wait till feeling hilarious, this might not get made. So we're just going to go with it as it is. And I apologize if it's not as entertaining to listen to. What is cataplexy? Cataplexy comes from Greek and Latin roots. In Latin, this would be cataplexa, which means to strike down with fear. And in Greek, this comes from cataplexis, which is the downstroke. During cataplexy, voluntarily controlled muscles go completely limp or significantly weaken without any warning, while the person who is experiencing it remains fully conscious. This leads to temporary, partial, or full bodily paralysis. These episodes are transient, which means they come and go. They last a few seconds to several minutes at a time, and they range in severity, frequency, duration, and the areas of the body that are affected. Cataplexic attacks are often triggered by strong emotional responses like excitement, laughter, sadness, anger, fear, or disgust. This is often associated with narcolepsy, but it can happen in isolation where the person experiences cataplexic episodes, but they are not a narcoleptic. Isolated cataplexy is a rare phenomenon, but it does occur under certain circumstances. In this video, I will be focusing on cataplexy and not the narcoleptic aspects that are often associated with it. Now, I am going to give some statistics right now about narcolepsy, but this is really the only area of the video where I will be touching on narcolepsy itself. About 1 in 2,000 people have narcolepsy, either with or without cataplexy. Up to 29% of young adult narcoleptics also experience cataplexy. The prevalence of people who experience cataplexy without narcolepsy is unknown. The onset of cataplexy may be the first symptom of narcolepsy that presents itself, or it might be delayed for up to 30 years in some cases. Most people who experience cataplexy notice the onset of symptoms in either adolescence or young adulthood, particularly when they are entering a new, potentially stressful environment like a new job or college or some major life event. So what does cataplexy look like in action? Often, cataplexy starts as a minor muscle abnormality or a barely noticeable weakness. This can be things like facial flickering or grimacing, unusual tongue movements, speech difficulty, drooping eyelids, jaw tremors or dropping of the jaw, head falling to the side because you're unable to keep it erect, muscles that twitch without cause. However, due to the variability in severity, episodes can greatly increase and even be mistaken for seizures or fainting. These can look like things like full body paralysis, drop attacks, slumping or falling to the ground, losing your grip on what you're holding and dropping things, or having your legs go weak and refuse to hold you up. Cataplexy can happen a few times a year or several times a day, varying from person to person and case to case. The individuals who experience these symptoms remain fully aware and conscious, are able to breathe, and can move their eyes. Now that we know what cataplexy looks like, I want to talk a bit about the anatomy and physiology of what is going on during cataplectic attacks. Again, we are working backwards, starting with the larger formations and getting smaller. The first bit of neuroanatomy I want to discuss is a system called Reticular Formation. The reticular formation is over 100 small neural networks throughout the brain that look like a net-like structure, which is what the reticular part of this name means. Your reticular formation is subdivided into two groups. Ascending reticular activation system, which is responsible for your sleep-wake transitions and alertness, the staying awake, your arousal. This reticular activating system has neurons that release dopamine, norepinephrine, serotonin, histamine, acetylcholine, and glutamate neurotransmitters. The second part of this system is called the descending reticulospinal tract. This tract is one of 4 tracts that work in coordination to control your movement and posture. The entirety of your reticular formation with the subdivided categories working together regulates your behavioral arousal, consciousness, attention, somatic motor control, muscle tone, cardiovascular control, your pain modulation from your lower body, your sleep, habituation, autonomic function, movement, and posture. The muscle weakness that occurs during cataplexy is caused by a decreased excitation of noradrenic neurons and an increased inhibition of skeletal motor neurons. Now, that's a mouthful. Basically, what that means is the noradrenic neurons in your brain, which coordinate with your sympathetic nervous system, which is the system that is overactivated in CRPS, are less likely to turn on. Now remember, neurons only have 2 options, on or off. There is no middle ground. It's firing or it isn't. So in your noradrenic neurons, less likely to fire. This is the same with your skeletal motor neurons. This increases their inhibition, which means excitatory transmitters would need to work harder to turn it on. One mechanism that has been hypothesized for why cataplexy happens is the activation of brainstem circuitry that normally creates atonia, which is the inability of your muscles to contract during REM. So like when you're dreaming during REM, your body muscles, for most people, don't move, so that you stay paralyzed while you're resting and dreaming. This system is thought to be activated while you're awake, which is what causes the complete muscular collapse. Again, this is a hypothesis, which means it has not been proved beyond a shadow of a doubt, and this is a thought process that is based on a limited amount of evidence to perpetuate further study. Cataplexy occurs almost exclusively in patients with a depleted level of hypothalamic neurons that produce a neurotransmitter that has 2 names, and I'm going to kind of use them interchangeably: hypocretin and orexin. For the most part, I'm going to be using orexin, even though I used hypocretin in the title. The exact underlying cause of this degeneration is unknown, but current evidence suggests that this is an autoimmune disorder, which would make sense when aligned with CRPS, because CRPS is an immunoneurological disorder where your adaptive and innate immune systems attack your nervous structures. The hypothesized mechanism for cataplexy is that an autoimmune response causes specific autoantibodies to form. Remember, autoantibodies are antibodies that are turned against the self. These autoantibodies target and kill the neurons in the brain that produce orexin. Before we talk about the area that produces orexin, I want to talk about one more location. This is the location of the brain that has the densest innervation of orexin nerves. This area is the locus coeruleus. Several neurodegenerative diseases are linked to a deficit of locus coeruleus neurons, and LC neurons do not discharge, which means they are not firing during cataplexic episodes. In Latin, locus coeruleus just means the blue place. The locus coeruleus is the major noradrenic nucleus of the brain. It sits right beneath your hypothalamus in the pons of the brainstem and is densely colored blue. The locus coeruleus is the primary site of noradrenaline in the brain, and it is activated by stress. It will respond by increasing norepinephrine secretion, which will in turn alter your cognitive function, increase your motivation, activate your hypothalamic pituitary adrenal axis, increase sympathetic discharge, and inhibit parasympathetic tone. This is the center in the brain that is responsible for the majority of your sympathetic nervous system. This is the main control center for that. Remember, your sympathetic nervous system is the system in CRPS that is way overactive. The locus coeruleus is a highly selective, extensive set of projections that cover widespread areas of the brain and spinal cord. It sends nerves and is connected to most structures of the neuroaxis in a highly specific manner. Your neuroaxis is the central nervous system of your spine and your brain. This section, your locus coeruleus, is inactive during REM and is part of your reticular activating system. Now remember, from the previous slide, we talked about how one of the hypotheses of cataplexy is that systems that are active during REM sleep get turned on during waking. That would include systems that are normally inactive during REM being turned off, which does align here with your locus coeruleus not being on during cataplex episodes. Your locus coeruleus controls a number of physiological processes, including the regulation of arousal, alertness, and autonomic function, including your sleep-wake cycle, attention, memory, cognitive control, your emotions, neuroplasticity, which is the ability of your brain to connect to itself and change, your behavioral flexibility, behavioral inhibition, posture, and balance. Your locus coeruleus is regulated by orexin, and it is the section of the brain receiving the densest innervation from the nerves that produce orexin in the lateral hypothalamus. So, let's talk about the area of your brain that produces orexin. The exact mechanism of orexin deficiency is unknown, but evidence favors an immune-mediated or an autoimmune attack, specifically targeting your orexin neurons. Again, CRPS is an immunoneurological disorder, so this makes sense. You only have about 10 to 20,000 orexin-producing neurons in your brain. Now that sounds like a lot, but the human brain has about 86 billion neurons. So it is just a very, very small fraction of the neurons in your brain that can produce this very important neurotransmitter. Most of these neurons are located in your lateral hypothalamus. The orexin system and your endocannabinoid system mediate many of the same cognitive and physical homeostatic effects. Remember, your endocannabinoid system is the system that responds to cannabis if you're taking it externally, and it is responsible for maintaining bodily homeostasis, which is your ability to stay in balance within yourself and between you and the environment. The orexinergic neural projections of the lateral hypothalamus are involved in many functions, including thermoregulation, which is the production of body heat, GI motility and function, the reduction of your sensation of pain, reward modulation, energy homeostasis regulations, neuroendocrine function, which is your brain hormones, and visceral organ function. As you can see, orexin is a very important aspect of your correctly functioning nervous system. Now, before we get into orexin itself, just a quick recap here. Orexin is produced in your lateral hypothalamus and is directly responsible for regulating the locus coeruleus, which is the major nucleus of the brain responsible for your sympathetic nervous system and activated by stress. Your locus coeruleus is a subpart of your reticular activating system, which is another subpart of your reticular formation. Your reticular formation is responsible for wakefulness, your sleep-wake transitions, control of movement, and posture. Orexin is a multitasking neurotransmitter that regulates many different functions. It is excited by reduced blood sugar levels and suppressed by elevated blood sugar levels. These are also known as your glucose levels. Some of the major functions of orexin includes the regulation of heat production and body temperature, the determining of whether an animal should be asleep or awake and active, increasing food cravings and suppressing the inhibitory post-ingestive feedback, which lets you know when you're full and to stop eating. It engages in situations of high motivation, controls the storage and release of energy, and protects against negative reactions to stressful stimuli. First, let's discuss brown adipose tissue activation. Brown adipose tissue is also known as brown fat, and it has an increased number of iron-rich mitochondria, which gives it that darker coloration. Brown fat maintains your body temperature through its thermogenic activity, which means it increases your body temperature by dissipating energy as heat. Your brown adipose tissue is innervated by your noradrenic fibers from your sympathetic nervous system, as well as having many blood vessels and capillaries for oxygen-rich environment. Adipose, whether white or brown, is used to store and synthesize energy, which is ATP. Brown fat has a mechanism to bypass the production of ATP via uncoupling proteins, of which it has several. This allows brown fat to produce heat without actually producing usable ATP that you can utilize for a muscle contraction. Brown fat is particularly inefficient for ATP production, but it is highly effective at producing heat to maintain a body temperature that is higher than the ambient temperature around you. Brown adipose tissue thermogenesis is induced by noradrenaline from your sympathetic nervous system, which is supposed to be regulated by orexin. Another major role of the orexin system is to integrate the metabolic, circadian, and sleep deficit influences. Your sleep deficit, which is the cumulative effects of not getting enough sleep. Orexin strongly excites various nuclei with roles in wakefulness, including your dopamine system, which is responsible for motivation and movement, norepinephrine system, which is responsible for your sympathetic nervous system, histamine, which works in your immune system and GI tract, and acetylcholine, which works in your parasympathetic nervous system. The excitation of orexin significantly increases the amount of wakefulness time a person will experience, decreasing both REM and non-REM sleep times. The inhibition of orexin neurons, which means making them less likely to fire, decreases the wakefulness time and increases non-REM sleep time. The loss of orexin neurons impairs the survival of long bouts of wakefulness, but this neuronal loss also fragments sleep by increasing the risk of awakening at the beginning of sleep and then reducing the likelihood of returning quickly to sleep. So you might fall asleep and maybe you're 30 minutes in and then you get woken up and then it's very difficult for you to fall asleep again, meaning that you're not getting REM, which is the restorative portion of the sleep cycle. The orexin system is also integral to appetite. The lateral hypothalamus, which is the area where orexin is produced, is a key site of regulation of food intake and energy balance. The hypothalamic nucleus is connected by and interdependent upon receiving, integrating, and sending out hunger signals to regulate appetite. Orexin signals cover the encephalitic regions involved in feeling hungry, feeling full, and the storage and usage of energy in body. Orexin is primarily there to modulate acute feeding behaviors, integrate multiple metabolic signals, and adapt to the energy demands of the body by altering wakefulness and feeding behaviors. We are also learning that orexin plays a large role in addiction. Orexin neurons are activated during situations of high motivational relevance, such as during psychological need states, exposure to threats or stress, or reward opportunities. This constitutes a broader, fundamentally unified role for the orexin system in facilitating motivational states, both positive and negative, and translating these states into behaviors that the organism uses to exploit a reward opportunity or to respond to a pressing threat. This process has been termed motivational activation. Orexin neurons translate this motivational activation into organized suites of psychological and physiological processes that support adaptive behavior, which means it makes you somewhat malleable so that you have associated responses to certain contexts and situations. This diverse integrative role must be the result of a heterogeneous function connectivity with wider brain circuits that allow the orexin neurons to modulate a wide range of behavioral and physiological outputs. The incoming and outgoing projection patterns of orexin neurons reveal that these cells are highly interconnected with key motivational and reward regions of the brain. External cues engage the orexin system, which in turn acts to translate these cue-induced motivations into positive or negative motivational reactions. Studies point to a unique role for orexin in, under conditions of enhanced motivation, driving the response for psychostimulant reward. A psychostimulant increases central nervous system activity by increasing neurotransmission of catecholamines and sympathetic adrenergic activity. An interesting thing to note is that narcolepsy cataplexy patients lacking these orexin neurons rarely develop stimulant abuse, despite long-term treatment with stimulant medications, including amphetamines. The orexin system also regulates lipid metabolism, which means it directly controls energy expenditure. Balance between the food that you intake and digest and the amount of energy that you utilize and spend during the day determines your long-term energy homeostasis, which is the balance between you within yourself and you within the environment. The neuromodulation of energy metabolism by orexin is a complicated and integrated process that involves several different brain regions. Orexin can act both centrally and peripherally on your nervous system to influence the lipolysis of white fat, increasing the non-exercise activity thermogenesis energy expenditure. The overall effect of orexin on this system is to promote a negative energy balance and reduce the amount of fat that you have on your person at a time. Orexins slow the onset of diet-induced obesity. Orexins also play an important part in regulating neurobiological systems that respond to stress. They are critical for protecting against depressive, anxious, or panicked reactions to stressful events. Reduced orexin levels correlate with increased depression, anxiety, and post-traumatic stress disorder. Elevated levels of orexins correlate to increased positive moods. The core symptoms of depression include feelings of despair, the inability to experience pleasure, and social avoidance. Orexin is also implicated in social memory, the ability to distinguish and remember familiar events from novel events, and fear-associated memory. A quick recap here. Cataplexic episodes are transient, variable periods of loss of muscle tone. The person experiencing a cataplectic episode retains consciousness, vision, circulation, and breathing capabilities. Cataplectic attacks are often triggered by strong emotional responses and are caused by neurodegeneration, likely from an autoimmune disorder. The major noradrenergic nucleus does not fire during cataplexic episodes, and reduced orexin and orexin-producing neurons cause a cascade of dysfunction. Despite major advances in understanding the disease mechanisms of cataplexy, therapeutic management is largely symptomatic for this disorder. Thank you so much for watching. Relevant sources, as always, are linked in the description below. If you would like to contribute to my medical expenses, my Patreon is CRPScontender. And if you would like to contact me on Reddit to suggest a topic you would like me to cover, or to just contact me to talk, I would like to have a more discussion-based, interactive community rather than me just kind of talking to the endless void. So if you would like to contact me, my Reddit username is right there as well. Thanks so much for watching. I hope you learned something, and I hope to see you next time.